Yeah. Oh, this stupid thing. Yeah. So rather than having him get 0 on the quiz, which seems useless. Stop looking at his quiz. Stop. Buzz off. Yeah. I had a teacher who would come around and like look over our shoulders while we were writing a test. It was like so distracting. It's stressful. I'm like, go away. It's stressful. I actually find when a student asks me a question that I don't immediately know the answer to, if I need to think it through, I find it very hard to actually think it through while I'm talking with them.
Hello, how are you?
I'm okay. How are you?
Good, good. I'm glad it's Friday.
Oh, Friday, yes.
I have to leave at 2:30.
Okay.
So just give you the heads up if there's anything
Yep.
I gotta take.
Just make sure you have a copy of the overall review. You may have gotten one last day.
I did get it
Perfect.
last day.
That's all we're doing, and the
Sweet.
notes are going to go up online, and I'm recording it, so
Sounds good.
you miss.
Awesome.
I like the hat.
Thank you.
Nice. I am dressed up as a person who had no time to think of about a costume.
It's like you can't breathe. But now this,
This is fine. This is great.
I don't know. Like when I'm not trying to try it out, it's neat.
Yep.
I don't know what's wrong with it.
Okay. If you did not pick up the equilibrium review, overall review, come and get one. So you have it for the weekend. Some of you might already have it, but some of you don't, so make sure you have one before you leave today. I have to say, I'm happy that you're wearing your jackets. Oh, okay, well, there you go. Oh, okay. Which one, who? Okay. All right, my friends, we gotta get going, otherwise we will not finish before the end of. So if you want to have a lab book in front of you, you can. You might not necessarily need one, but if you want one, they are back for that. Okay. You will also probably want a lab booklet out, so we're gonna grab that.
Okay, let's see. Anybody join me here? Let's see. No, nobody joined me. Well, no, Yura's not here and she wanted to join us, so I'm wondering if she's having difficulties, but yeah? No, she had things. It was a thing. She spoke to me about it. Okay, anywho, we have, and how much do you learn when you're at home watching a screen compared with how much you learn when you're here? Like, it's just, I don't know. Pardon me? Some people did fine with it. I mean, my son did first year university all online, and he somehow survived it. I don't know how, but yeah. Anyway, we are going to be looking at part 1. And where our first equilibrium then is the Brom-Cresol grain. And we are going to use the initials B, C, G to represent Brom-Cresol grain, because the actual formula is long and complicated and nasty, okay? So, Brom-Cresol grain comes in 2 different forms. And you'll probably want something to write on, unless you just want to like chill out and be like, it's online anyway, so you can download it later. One form of Brom-Cresol grain has a hydrogen ion attached. And that form is yellow. The other form of Brom-Cresol grain does not have the hydrogen attached. The hydrogen comes off, and when it doesn't have the hydrogen attached, it is a different color. It is blue. Do you remember this one? This was in the Erlenmeyer flasks, between the blue and the yellow. Now, the system started out blue. Therefore, what was favored if it started out blue? Products are favored, okay. If the system started out blue, then the products are favored. Okay, products. And now what we did is, the first thing we did to this system is we added some HCl. What kind of a compound is HCl? It is a covalent compound. It is also, somebody said it earlier, acidic. It is an acid. How do we know it's an acid? It has that H. Yes, so we know it is an acid. What do acids do? In solution? They dissociate. Yes. And now I am going to get you to write a dissociation equation for HCl. And it starts out, before it's dissolved in water, it is a gas. and then we dissolve it in water, and you're going to write what happens once it goes into the water. And I'm going to come around and take a look and see what you're remembering, or if you need a little hand with anything. No, we're not doing anything just yet. We're taking a holistic view, and we will be zeroing in on some things soon. You know what? You don't need to write one everything, but maybe like if you're ready to associate things, get that. Yeah. Oh. Okay, we're going to go over this. So if you're stuck, it's okay. What happens is it dissociates. To dissociate means to break into. And so we have one half of it is the hydrogen ion, and the other half is the chloride ion. And because it is dissolved in water, the state is aqueous. This is not the last dissociation you're going to do today, so that gives you an idea to remind yourself what we're going to do. Now, HCl in particular is a strong acid. And therefore, it dissociates fully or completely, okay? And that is why that arrow right there is a one-way arrow. question. What is the stress when we add HCl to our system? Yeah, it's a change in concentration. A change in concentration of what? Your reactant is HBCG. So whenever I ask about a stress, it has to be one of the species in the reaction. Yes, so you would either be dealing with HBCG or BCG minus or H plus. And in this case, because we added HCl, the ion that we are dealing with is the hydrogen. Yeah. Okay, and so we changed the hydrogen ion concentration. We didn't just change it. Did we increase it or did we decrease it? We increased it because we added H plus. Does that make sense? We put in HCl, it made H plus, and that means that our hydrogen ion concentration has increased. As a result of hydrogen ion concentration getting bigger, which way will this equilibrium shift? It's going to shift to the left. And therefore, what color will it turn? It will turn yellow. Okay. Did anybody get an intermediate color in between the yellow and the blue? Did anybody see? I'll wait till you're finished writing. Yeah, I think at least some of you got a green color, yes? Some of, yeah. And if that's the case, how could we have gotten a green color? Yeah, you've hit a point, a position of the equilibrium where you have a fairly equal concentration of products and reactants. So you have a similar concentration of yellow reactants and blue products, and that's why you could end up with that green color. Yes? Don't worry, just, we saw a green color because at that point, there was approximately equal concentrations of the reactant, which was yellow, and the product, which was blue. And of course, yellow plus blue gives us green. Do we all know our color combinations? I'm going to review them because every year there's one or two people whose kindergarten teachers didn't do them a service and didn't teach them. Or you can't see them, that's the other way too. Okay, so yellow plus blue gives us green. Huh? What happened? Oh no, we're good. I think Yura's just joined us. Hello, Yura. Yeah, there she is. We're good, I think. Oh yeah, you were asking. Yeah, no, Yura's joined us. Hello, Yura. And then me. I don't have my chat up, so if you're typing something in, I can't see it. And now I'm gesturing at the screen as though it were a real person. So I'm just going to stop doing that because that's crazy. Okay. Yellow plus blue gives us green. What are my other color combinations? Red and yellow gives us orange. And what else? Red and blue makes purple. And if you haven't played around with food coloring, you can go buy yourself some food coloring for pretty cheap, or some watercolors at the dollar store, you know, and just mess around with them and combine your colors so you can see them, right? All right. This substance, Brahm Cresol green, because it has a different color when it's in the presence of an acid and when it's in the presence of a base, it is called an acid-base indicator. Oh, I haven't shared my screen. Oh. Oh. Dang. Okay, hang on. How do I make it bigger? That's not bigger. Bigger? Bigger. Bigger. Down there. Okay. Bigger. Share screen. Share screen. Oh, there we go. Yura, don't worry. Everything is going to be up on our teams. My apologies. Okay.
Thank you.
Is an acid-base indicator. There we go. And where was I? I don't miss doing hybrid lessons. It's too many moving pieces for my poor little brain. Anyway, it's an acid-base indicator, which means it changes color depending on the pH. Can you, thinking back over things we've done, can you remember another acid-base indicator that we have used? Yeah. Can you remember which lab we did it in? That first one, our titration lab. What were the two colors? It turned between pink and colorless. And the indicator, if you look on page 7 of your data booklet, see if you can find it. Yep, page 7 of the data booklet. Anyone need a data booklet? Yeah. Yeah. All right, so what is our pink to colorless indicator called? Phenol. And then it's got this pH that's silent. Phthalene. EIN. It's another one of those exceptions to the IE rule. phenolphthalein. It always makes me think of Sylvester the pussycat. But you don't actually say the pH in there, you just say the TH. So it's not quite as exciting. Anywho, the reason that phenolphthalein is such a good indicator for a titration is, can you imagine if you were trying to titrate something and your end point where it changes color, say we were using bromcresol green. Do you go with the teal green? Do you go with the yellowy green? Where's your greenest green? Do you know what I mean? Like it's really hard to tell. Whereas if you're dealing with pink and colorless, the moment it turns even a little bit pink, you know you're done. Yes? So, second thing we did to our equilibrium, HBCG in equilibrium with BCG minus plus H plus, and everything is aqueous. Second thing we did is we added NaOH. What kind of compound is NaOH? Yes, it is a base. And it's a base because it contains the OH minus ion, the hydroxide ion. And one thing to note is that sodium compounds, can you go look on your data booklet on page 4? I think it's page 4. Yep, page 4. What can you tell me about all compounds that have sodium ions in them? They're all soluble because sodium is an alkali ion. See how I'm working in the next unit here as well? All about solubility. Oh, always very meta chemistry. All right. So Na plus compounds are all soluble, and that's why we chose to use sodium hydroxide rather than something like magnesium hydroxide, which is not very soluble. So because it is soluble, we can ask ourselves, what does NaOH do in solution? It dissociates. What am I going to get you to do? Please write the dissociation for NaOH. And it starts out as a solid before you dissolve it. So one thing about polyatomic ions, of which a OH is a polyatomic ion, we have Na plus, which is aqueous. OH minus is aqueous. Polyatomic ions never split apart. When you have a dissociation, you should only ever end up with two different products. Okay, dissociation. Only two different products. Of course, there are exceptions to that, but for grade 12, no. Okay? You can just pretend I said there were no exceptions. All right. So if that's the case, how do the Na plus and or the OH minus affect our system? And our system is HCCD in equilibrium with H plus and BCG minus. There we go. Chat with your partner, see what you can figure out. I know you're all. Is sodium going to affect our equilibrium? No, because sodium is soluble with everything. It won't, it's just a spectator ion. How about the OH? Can our OH do something? Yeah? What can it relate to in this equilibrium here? Yeah, it can react with our H. What do H and OH do when they get together? Yeah, they make water. So we have H plus OH minus gives us water. And if that happens, we are using up H plus. So what is our stress then? Yeah, the stress is a decrease in the concentration of H plus. And if it has decreased in concentration, which way are we shifting? We're going to shift to the right. Yeah? And it will turn. This was yellow. This was blue. Blue. All right, we're almost done part 1, but we do want to look at analysis number 1 because that question is usually not very well done by students because they only kind of give me half the answer. So we're going to look at it. So you'll give me the whole answer. And ooh. Analysis number 1, how would increasing the molarity of the NaOH from 0.01 molar to 0.1 molar affect, this is on page 169, so if you don't want to write it down, it's on page 169. Affect the number of drops needed to get a color change. Now make it quantitative. We need less drops, yes? Do we agree? Now I have a challenge for you. Make your answer quantitative. Anyone wanting an explanation of why it's less drops? Yeah, because this one is more concentrated, yes? So if we want you to make our answer quantitative, 10 less drops? You're on the right track. Because when we took our concentration from here to here, how many times more concentrated did it become? 10 times more concentrated. So does that mean we need 10 less drops, or does it mean something else? It's the ratio. So how many, what? 10 less drops? A tenth. Yes, we need a tenth. We need 1/10 of the original number of drops. Does that make sense? Because every particle, every drop contains 10 times as many NaOH particles. Yes? Only only if you can. That's the only one where I think it's important because they actually gave you numbers, right? And if they're giving you numbers, you can assume that, oh, maybe I should be doing something with numbers too, right? Yeah. I don't think there's many like that in here. This is mostly a qualitative lab. Therefore, we need only 1/10 the number of drops. Now, we are doing this in an informal fashion here, scribbly, scribbly all over the place, whatever. You are going to write your answers either in full sentences or in very clear point form. Yes? So in either full sentences or in very clear point form. Either way, I need to know what the question was asking. I need to be able to tell. No. Some people like to write the question because then they don't have to think about how to phrase their answer, which is fine. But you know, if you can phrase your answer, it saves you writing, right? I need what the question was asking. Part 2. Oh boy, we're only going to get through part 1 and 2 today. It's a long lab. This is the lab that's going to last for a month, right? Well, I don't know about that because we started 2 weeks ago, and then if it's not due till later next week, it'll be like 3 weeks, right? So yeah, it's pretty long. Okay, part 2, we have our equilibrium. And that one was with our iron, which is yellow, 3+, plus our SCN, which was colorless, in equilibrium with FeSCN 2+. And do you guys remember what color that one was? Appropriate for Halloween, it was blood red. Although orange, we diluted it to a light orange, yes. So, let's see. We mixed FeCl3, iron 3 chloride, and potassium thiocyanate to make the above equilibrium. Where did the Cl and the K go? They didn't dissolve? Turn into gas and left the open system? I mean, they're not bad guesses, but they're not correct. But they're not bad guesses. I like people guessing. Guessing's good. Guessing means you're thinking and not falling asleep, which I'm trying hard not to do. Any guesses? Not a bad guess. Okay, I'm gonna take us away from that question for just a moment, and we are going to write, we're gonna come back to it, the dissociations for FeCl3. Keep it to yourself. Keep it a secret. We're gonna make sure, see if anyone else can get it, okay? We're gonna dissolve this in water, and we're gonna take our KSCN, and we're gonna dissolve it in water. And remember, how many different things should I get after dissociation? 2, okay? So if you're looking at the KSCN and you're like, I don't know what to do with that, check out your table of polyatomic ions. Yes, on page 3, if you need to. It's okay, don't worry. So if I didn't get a chance to check your finished work, we're going to go over it anyway, so that's okay. So a couple things to watch out for that I saw in both this block and my other block is I saw a lot of this goes to Fe3 plus Cl minus, and the problem with that is that you were starting with FeCl3, so that's unbalanced, yes? The second thing that I saw that was a little bit of a problem was some people put the 3 down here. What that would mean is that you would have 3 Cl's kind of in a little clump all bonded together. Okay, that's what that would be. And that's not what actually happens in solution. What happens is they all separate out into, you have an Fe3 plus, and then all 3 chloride ions float around separate from one another. So you would write instead Fe3 plus 3 Cl minus. When you put the number in front, when you have a coefficient, that means they're separate from one another. If you write it as a subscript, that means they're attached to one another. And then the K is going to be by itself, and you can find on page 3 of your data booklet is actually the very last polyatomic ion there is the thiocyanate ion. Okay, and that is our dissociation. So now taking a look once again at our equilibrium here, we started out with FeCl3 and KSCN, but what we really started out with is Fe3 plus and 3Cl minus and K plus and SCN minus. So what happened to my Cl and my K? Yes, they are spectator ions, so we don't actually write them in the equation, okay? Because they're not in my equation. I mean, honestly, that's what it comes down to. They are there, and they're not in the reaction. So therefore, they have to be spectator ions. You could, from the fact that potassium really doesn't react with much of anything, it's another alkali, so it's soluble with everything. Chloride is also usually quite unreactive. Not always, but most of the time. Okay, so SCN, woo, and Cl minus are spectator ions because they are not in the equation. Okay. K and Cl minus. Oh my gosh. See, you guys think you're tired? My brain is just spitting out random ions all over the place. Yep. All right. So now we're going to use all this information that we have to do the following. To our equilibrium, we added KSCN. And I'm going to rewrite our equilibrium here. SCN minus in equilibrium with FeSCN 2 plus. This is yellow, and this is colorless, and this is blood red. When we add our KSCN, what is the stress? It's an increase in the concentration of what? Is it an increase in the concentration of iron or SCN or FeSCN? Because it has to be one of those. SCN, excellent, okay. Yep. What's the K doing? It's not reacting. And if it's not reacting, what is it? Not reacting, therefore spectator. Okay. Oh, and I forgot my minus in there. That was bad. Okay. So if we increase our concentration of the SCN, which direction does this thing shift? It shifts to the right. And therefore, what color do we see? Blood red. Okay. All right. Our second thing we're going to do. We are going to add FeCl3. I can give you more paper. I'm not sure my value is line paper, but I've got tons of online paper. What's the stress in our system? That would be the color. Our Fe, yes, we have increased our concentration of Fe, 3+. Therefore, which way does our equilibrium shift? Yep. And what color will we see? We will see blood red. I'm just going to make a note here that there will be more yellow stuff than before also, because when you increase the concentration, come on, it's lagging. Okay, when we increase the concentration of iron, it does come back down, but not quite to its original level, yes? So the iron concentration is actually higher than before, yes? So we actually have more yellow stuff than before. Because iron 3+ is yellow. Well, the blood red is so dark, it just masks the yellow color, okay? Are you good? It's so dark, it masks. It makes the yellow get so blood red, it makes yellow. No, that would not make sense. It masks the yellow color. Alrighty. Whew. We got 2 more to go. Do we have time? We might. We'll see. Yeah, 9 minutes. Let's go for it. Okay. Number 3, we're gonna add some KCl. And I'm going to rewrite our equilibrium here because it's disappeared once again. Red, yellow, all over left. What do we get when we put KCl into water? We get K plus and we get Cl minus. K doesn't react. K is soluble with everything. It's an alkali. What about our Cl? It does nothing also. Also does not react. Therefore, what can we say that the system will do in response to adding KCl? There's going to be no stress, therefore there will be no shift. If you did see the yellow color getting lighter, it would only be because we were adding a clear solution and maybe it just got a little bit diluted. Yes? So if you saw it get lighter, it was just because of dilution. Okay? So yeah, we just added some spectator ions and they did nothing. Huge shock. Okay, now this last one is going to require a little bit of thinking. What if we add some NaOH? And remember, it dissociates into what? Na plus and OH minus. And Na plus is what kind of an ion? It's a spectator ion because it's an alkali. Always soluble. Now, what about this OH? I would like you to take a look on page 4 of the data booklet. To see if you can find some way that this could affect our equilibrium. Yeah, it's soluble with your alkali ions, with hydrogen, with ammonia. Sorry, not ammonia, ammonium. So if we go to our data booklet and we look, we've got, oh, there it is, hydroxide. It is, if we had strontium or ammonium or hydrogen, it would be soluble, but with everything else, it is low solubility. Do we have an all others ion in our reaction? Yes, we do. What do we have? Which one would be likely to react with OH minus? The iron, okay? The iron is going to get together Fe3 plus OH minus, and in fact, not just one OH minus. How many will I need? I will need 3 of them to balance out my charge. And this is a precipitation reaction. And we get FeOH3 solid. So what is our stress? Of what? OH is not part of our equilibrium. You have to be changing one of the concentrations in here. We're changing the concentration of iron. What are we doing to the concentration of iron? Are we increasing it or decreasing it? It is reacting and it's becoming part of a solid. If it's a solid, is it aqueous anymore? No. Therefore, what is happening to our concentration of iron? Concentration of iron goes down because it's being used up in this reaction. And therefore, the concentration of iron goes down. And if it goes down, which way will the equilibrium shift? It's going to shift to the left. And if it shifts to the left, what color does it turn? Turn